Hello and welcome back to the lecture on applied econometrics. We have been talking about types of regressor. In the previous lecture, we spoke about non-stochastic regressor and we said that that is somewhat unreal. Now, in this lecture, we are going to talk about stochastic regressor, which is more close to reality, but there is a cost, right? Because the moment I talk about reality, there is more, it is going to be more complex, and we are going to see the problem or the kind of challenges that we might face when you actually take a stochastic regressor instead of a non-stochastic regressor. So, to begin with, what is a stochastic regressor? Stochastic regressor is a regressor that the values of the regressor is actually the values of x are drawn randomly from a population of finite mean from a population with finite mean and a finite non-zero variance Now, what do I mean by this, particularly this non-zero variance? So, as I said, the moment I say the regressor is stochastic, that is all the regressors xi's, they are stochastic. So, I essentially allow a sort of randomness into the values of the x, right. So, I no longer actually determine the values of the x and give it to assign it to the x variables when I run the regression. Now, here since I am allowing some amount of randomness, if I have a non-zero variance. So, if I have a zero variance, so that would mean there is no variation in the data, and that would mean that the component of randomness will go away. So, essentially it has to be a non-zero variance. Okay. So, that is the first thing that we need to remember. Okay. Now, when I say that they are stochastic, they are random, so then I will actually allow the regressors to actually vary together. So, there could be a joint probability distribution of the regressors, which were actually absent in the previous case. In the previous case, we assumed all the xi's are independent to each other, and here we are allowing a joint probability distribution of the xi's. Okay. Now, that is a really relaxation, but at what cost? So, I will talk about that. So, the moment I actually relax this, what is going to happen is that you can no longer ignore the possibility that the xi's are also, or rather may also be related with the error term, and that is a problem. So, essentially in the previous case we were having, when we talked about the unbiasedness of the estimator, of the regression estimator, we were assuming that xi's are required to be independent of the error term, but the moment I allow the joint probability distributions among the xi variables, I also create the possibility that xi's may be sort of related to the error term. Okay. And the moment I allow the xi and the error term to covary, so at that point the bias, the condition of best linear unbiased estimator might actually get violated. And how is that going to happen? Let me actually show you. So, essentially what I am saying here is that I cannot say expectation of, let us say, some xi ui, I cannot say it is equal to expectation of xi and expectation of ui. Okay. I cannot say this, or in other words I cannot say this is equal to 0, okay, because if it has to be 0, then the expectation of ui has to be 0, and even if expectation of ui is 0, if this condition does not hold, I can never get this value, right. Now, as I claim that because of this, because they are not independent, because xi and error term are covarying, the bias is going to exist and how the bias is going to exist. So, let me actually sort of derive the bias term, okay, how the bias is going to come to play. Now, we know by definition that B 2, which is the estimated regression coefficient, is equal to summation x I minus x bar into y I minus y bar divided by summation of x I minus x bar, and where I is equal to let us say 1 to n, okay, and this of course a whole square, I equal to 1 to n. Okay. Now, if I let us say substitute the values of y I, what I will get is, and we have actually done it previously, I is equal to 1 to n x I minus x bar, and here I will have let us say beta 1 plus beta 2 x 2 or beta 2 x I plus u I minus beta 1 minus beta 2 x bar minus u bar, right. This is something we have done previously, and it is of course will be divided by the whole term I is equal to 1 to n x I minus x bar whole square, I is equal to 1 to n. Okay. Now, we know what is going to happen. So, beta 1 is cancelled, I will have a beta 2 here, I will have a beta 2 here. So, what I am going to do? I am going to take, so let us say beta 2 out, and then I will have summation I is equal to 1 to n x I minus x bar, and this is also going to be x I minus x bar. So, x I minus x bar whole square by summation I equal to 1 to n x I minus x bar whole square. Okay. And then I will have, on the other hand, I will have all this u I and u bar present. So, it is going to give me summation x I minus x bar u I minus u bar, okay, and that is divided by x I minus x bar whole square, I is equal to 1 to n. Now, the first term is going to be this numerator and denominator cancel out. So, I will have beta. So, essentially I am going to have beta 2 plus summation of x I minus x bar into u I minus u bar divided by summation of x I minus x bar whole square, and it is over all n. Okay. Now, I have actually shown previously that this could be, this value could be represented as a I, okay. And if I take x I minus x bar u I minus u bar over all n, so then I will have something like, I can actually prove this, summation x I minus x bar is equal to into u I, because u bar is actually constant. So, basically if you multiply, so then essentially you will have u bar to be, you can actually take a basically sum of all the errors, and that will give you a 0. So, essentially you can represent the numerator as this, and let me actually write down the equation number 1, 2, and using 1 and 2 I can actually say, let us say this is 2 and this is 3. So, using 1, 2, 3 I can actually say this is equal to beta 2 plus summation a I u I. Okay. So, this is something that I wanted to have. Now, this is, let us say this is equation 4. Now, from my equation 4, now if my, now go back to the previous condition that we have seen, if the x i's are related to the error term. So, if x i's are related to the error term, what will happen, let me use a different color, what will happen if they are related. So, if I take an expectation of beta, B 2 here will be expectation of beta 2 plus expectation of summation of a I u I. So, this is going to give you a beta 2, but this one is not going to give you a value of 0, okay, because a I and u I are they are correlated. So, they are covariant. So, as long as they are covariant, you cannot write this is equal to, let us say, a I into expectation of u I or something like that. You cannot write that. So, if you can't write it, so you, and if you could have written that, so you could have gotten the value expectation of u I is equal to 0, but you cannot do that now, and because of that you will have a bias term. You will have a bias term, which is actually a problem. And if you have a non-stochastic regressor, so then you do not have any problem So, this is for the stochastic regressor, this is for a stochastic regressor, but if it was non stochastic, you could have written this is equal to a I into summation into expectation of u I, okay, and that would have been 0, and then your bias term would have gone from the basically estimator. Okay. So, essentially that is the problem. So, the moment you actually have this xi related correlate covariant with the error term, you actually have a bias term, and the moment you have a bias term, your estimator is no longer going to be a blue estimator. You want a blue estimator, right? So, it is not going to be a best anymore. So, that is a problem, and we sort of need to actually take care of that, and that is why whenever we actually deal with stochastic regressor, we make another assumption. That is an you know, there is an addition to the other assumptions that we make for you know, estimating regression. So, this assumptions that we are going to make is that you need to have xi and ui's are required to be independent. Xi's and ui's are required to be independent, okay, and you write it expected value of ui given all xi is equal to 0. Okay. So, mean value of the error term given all xi is equal to 0. So, that is what you sort of assume. So, if your assumption is correct, if you can actually make this assumption, then your stochastic regressor will behave in a way your non-stochastic regressor actually behaves, and that is why whenever you are dealing with stochastic regressor, you need to make this extra assumption that we have just derived. Okay. And when you do that, what you will have is you will actually have covariance of xi ui is equal to 0, okay, or also you can say expectation of ui is equal to 0. Okay. So, which are basically you need to have for your regression equation. So, with this we will end the lecture on stochastic regressor, and in the next lecture we are actually going to talk about you know, the assumptions that we have been dealing with for all the past lectures in the second module. So, all of these you know, the exercise that we have done will culminate to some assumptions, and we are going to talk about all the assumptions in one go. So, we will deal with the stochastic regressor and non-stochastic regressor and their corresponding assumptions in the next couple of lectures. Thank you.